All right, this review covers arc length and different integration techniques and also L'Hopital's rule. So the first part says find the arc length of the function over the given interval, and this is calculator allowed. So you need to memorize the arc length formula. There is arc length on both calculator and non-calculator. So if you want to practice non-calculator, go back to the assignment number 1 where we had plenty of that. Okay, so anyway, this is f of x equals or y equals. We need f prime of x or dy dx. So 4/5 times 5/4 will be 1, and then this will be x to the 1/4 if I subtract 1 from the exponent. And then the formula calls for f prime of x squared. So when you raise x to the 1/4 to the second power, you multiply your exponents, you get x to the 1/2. And the arc length formula is s equals the integral from, we're on 0 to 4, of the square root of 1 plus f prime x squared, so x to the 1/2, dx. And we need a calculator for this one because we wouldn't have enough information to do u sub with it. So I'm going to hop over to my calculator. 0 to 4. Square root of 1 plus x to the 1/2 is square root of x. So I'm getting approximately 6.076 for that first arc length. Okay, same thing for the next one. We have a y equals. We want to get dy dx first. So 3 times 1/6 will be 1/2 x squared. And then this is like 1/2 x to the negative 1. So that's going to become minus 1/2 x to the negative 2, or I'm just going to put x squared down here. And I want to square this. So although if I'm using a calculator, I guess I really don't need to go through all of the work. If a calculator is allowed, then I could just get down to the integral from 1 to 3 of the square root of 1 plus this whole thing squared. I could just type all of that in and save myself some algebra. If I didn't have a calculator, I would need to get a common denominator so that I could more easily square this and then continue to work. But I'm just going to leave it like that. So, math 9, 1 to 3, square root of 1 plus, so I'm going to need parentheses here, and then it's x squared over 2 minus 1 over, now I didn't use the fraction key, so just be careful here. 2x squared has to be in parentheses. Or remember, you can use, let me finish this out. Remember, you can use alpha y equals, and that will give you a fraction so that if you type in 1 over 2x squared, the calculator understands that the 2x squared is in the parentheses, or is in the denominator. Okay, so this one was 3.383. Okay, so that's our little arc length reveal. Now we have integration. So this covers sections 8.1, 8.2, and 8.5. So we're thinking of all the methods here. So remember, your first thing is like, does u sub work? Or is it arctan or arcsine? Or do I have to do integration by parts? The final thing is that it could be partial fraction decomposition. So part of your studying should be going through and looking at looking at the different homework assignments. So when the problem looked like this, we did partial fraction decomposition. When it looked like this, we did integration by parts, etc. So I'm going to try u sub here. Anytime I notice a difference of 1 degree between things, that's usually u sub. So u is equal to x squared minus 36. Du dx is equal to 2x. So du over 2x will equal dx. So if I sub out this dx and I put in du over 2x, that works because this x cancels with this one. This whole thing is u. I don't know why my pen is writing strangely. So there is a 1/2 constant out in front of the integral, and then it's just square root of u du. So when I integrate that, this is u to the 1/2, so it becomes u to the 3/2, and we divide by 3/2 or multiply by 2/3. And then I'm just going to clean it up and put my expression back in for u. So these 2's cancel. So we're going to get x squared minus 36 to the 3/2 over 3 plus c. All right, for the next one, u sub is not going to work here because if I let, same thing's going to happen as I had before. Du, well, no, wait, u sub, yeah, I'm sorry. U sub will work here because the x will cancel out. I was looking at this as x squared. Okay, so take a look at this. We've got u equals x squared minus 49. I wonder if this would also work with partial fraction decomposition. Maybe we'll take a look at that. Du divided by 2x would equal dx. So, yeah, so this is okay. Du divided by 2x. X is canceled. This is u. There's a 1/2 now. So now it's 1/2 integral of 1 over u du. And that's 1/2 times the natural log of the absolute value of x squared minus 49 plus c. I was looking at what if you did partial fraction decomposition. I just want to get into that because why not? So what if we did, okay, this is something over x plus 7 and something over x minus 7. If I use that cover-up method, you're plugging into x over, so it's like x, find a spot to put this, over x plus 7, x minus 7. So let's see, if I plug in negative 7, I get negative 7 over negative 14 because I'm covering up the x plus 7. So I would get 1/2. And if I did 7, I get 7 over 14. I think I get to the same answer. That's 1/2. 1/2 ln of x plus 7 plus 1/2 ln of x minus 7. Yeah, same thing. So this would work too. I'm not going to finish that problem off, but yeah, that is the same idea for that one. Okay, we have to integrate something with a natural log. And remember, if a natural log is involved in the integral and there's no x down here to cancel out for u sub, this is going to be integration by parts. So let's set up our tabular method, u and dv. U would have to be, because of Leate, u has to be ln of 2x. And then there's really just like a 1/2 dx. Or the 1/2 could be with the ln as well. It doesn't matter. So the derivative of ln of 2x is 1 over 2x times 2. And the integral of 1/2 dx is 1/2 x. Put in your plus, put in your minus. With natural logs, you only do one round of this. So far this comes out to 1/2 x times natural log of 2x minus the integral of, 1 over x times 1/2 x. I'm going to clean that up for sure. This part that's not in the integral will need to get evaluated. I'll do that in a minute though. So we have this so far. 1/2 x ln 2x. That's going to get evaluated from 1 to e. And then this is like having a 1/2 out front. The x's cancel, right? This is just the integral of 1/2 dx from 1 to e. Okay, so now this whole thing can go in here. 1/2 x ln 2x minus 1/2 x. Both of those are getting evaluated from e to 1, so we might as well just do it all at once. So this is, when I plug in e, I get e over 2 times natural log of 2e minus 1/2 e, or minus e over 2. Minus, when you plug in 1, you get 1/2 ln 2 minus 1/2. Now, I'm not going to simplify that any further. I'm just going to leave it like that. If I were looking for a multiple choice answer, maybe they would do a bit of factoring or something, but I don't think we have anything that crazy. Number 6, you should recognize from the partial fraction decomposition homework. This is kind of our classic e to the 2x sine 3x. So this is one where we're doing integration by parts again. And you let, because of Liate, you need to let u equal the trig piece. And dv will be the exponential piece. So remember, the number of rounds should be 2. We just need to get back to a sine function for derivatives. So if I take the derivative of sine 3x, I get 3 cosine 3x. If I take the derivative of that, I get negative 9 sine 3x. So I'm back to sine, so I'm done. When I integrate e to the 2x, there's going to be u sub happening, and you're going to end up with a 1/2 e to the 2x. If you're not sure, if you can't remember that rule, then you need to actually do the u sub off to the side somewhere. When you integrate this again, you're going to get 1/4 e to the 2x. Assign your plus, minus, plus. This part is going to be an integral, and it's going to be minus 9/4 e to the 2x sine 3x. Okay, so this is an indefinite integral. There's nothing to evaluate, so we get it to, let's see, I'm going to try to condense this as much as I can. So e to the 2x over 2 times sine of 3x. So that's the first term. And then it's minus 3/4. There's an e to the 2x up there. Oops. Make this not look so sloppy. There's an e to the 2x up there and a cosine of 3x up there. And then the last piece is, I'm kind of out of room here, so I'm going to write it down here. Minus 9/4 times the integral of e to the 2x sine of 3x. So the reason that on these we stop when we get to a sine 3x is because this integrand is the same as this integrand. And so we can go ahead and add 9/4 times this integral over to the left side. So 1 plus 9/4 is 13/4 times the integral of e to the 2x sine 3x dx equals everything I have left over here. Sorry, there's not much room to work in here. You can always use extra paper if you want. And then we need to get rid of the 13/4 by multiplying by 4/13 on both sides. 4 over 2 is 2 over 13. So 2 e to the 2x sine 3x. 4 over 4 cancels, so minus 3 over 13 e to the 2x cosine of 3x. And remember to put in the plus c because that's an indefinite integral. Okay, these are my favorite. This is by parts, and I have something algebraic, so that's always the best. So u and dv. So u has to be the algebraic part, and dv has to be the exponential. Take derivatives until you get 0. So the derivative of x is 1. The derivative of 1 is 0. Integrate e to the 3x. You'll get 1/3 e to the 3x, and then 1/9 e to the 3x. Assign plus, minus, plus. Connect diagonals. This would be the integral of 0, so we don't need it. So this gets us right down to the answer. That's why I like these. So this is going to be, in the numerator, we have x e to the 3x over 3 for the first term. Then it's minus 1/9, so minus e to the 3x over 9. And the last part is a 0, so just plus c. Nothing left over to integrate when you have an algebraic piece. All right, now number 8. I could I could try separating this out or doing some sort of weird U sub like I did for this one, but U sub was easier when I just had a single x up here. When it's x minus 39, it's a good idea to do integration or partial fraction decomposition. So anytime I notice that the denominator factors and I have more than just an x up here, I have multiple terms up here, I can do this cover up method. So remember, this allows us to get this into something times 1 over x minus 4 dx plus or minus something times 1 over x plus 3 dx. And once we get those coefficients, these are really easy to integrate. It's going to be something natural log of x minus 4 plus or minus something natural log x plus 3. So plus c. So the only thing I'm missing are these constants out in front. So to get them, remember you use the cover up method. So I'm to find when x equals 4, I'm covering up x minus 4, and I'm plugging into x minus 39, so negative 35 over x plus 3 over 7. So that's a negative 5 out in front. So negative 5 out in front here. And then for the next one, I let x equal negative 3 because of the x plus 3. Cover up the x plus 3. Plug negative 3 into x minus 39, so that's negative 42 over negative 3 minus 4 over negative 7. That divides out to positive 6. And yeah, that's it. You might be looking for a multiple choice answer that gets condensed, but otherwise we can leave our answer like that. Okay, for number 9, x times x minus 1. So u sub is not going to work for this one. We had one like this in our homework for integration by parts. U sub doesn't work. It's not inverse trig because the square root's not in a denominator. So you can still try integration by parts. This is a product. These both kind of seem algebraic. So when you're deciding like what are you going to let u be, pick the algebraic piece that will actually get to 0. X, when I take a couple derivatives, will get down to 0, whereas x minus 1 to the 1/2 will not. All right, so the derivative of x is 1. The derivative of 1 is 0. When you integrate this, you're going to add 1 to the exponent. You'll get x minus 1 to the 3/2, and then it'll be times 2/3. And then do that one more time. So when you, give myself some space here. So when you integrate this, this is going to become x minus 1 to the 5/2 divided by 5/2. So 2/3 times 2/5 will be 4/15. And then we do plus, minus, plus, connect diagonals, loop around, integral of 0. And we should get right down to our final answer then. So this is going to be, what do we have in top? We have a 2, we have an x minus 1 to the 3/2. Only thing in the denominator is a 3. And there's a minus here, minus. We have a 4, x minus 1 to the 5/2 over 15. And there's no final integral, there's just plus 0, so this is going to be plus c. Number 10, u sub won't work because there's no x to cancel out in the numerator. But I do see a difference of squares under a square root, so that should be an alert that you're doing arcsine. So a squared is 100. That means a is 10. U squared is x squared. U is x. Du is dx. Du dx is 1. So that's just going to be a du. The 100 can go out in front. So this is 100 times the integral of 1 over the square root of a squared minus u squared du. And that's arcsine. So the integral for this will be just arcsine. It's no 1 over a. So arcsine of u over a, so x over 10, plus c. Okay, for number 11, we have cotangent squared, which is not the derivative of anything, so we need to use some trig identities. Remember, you know that 1 plus tangent squared equals secant squared. And if you just put cos in front of those, you get 1 plus cotangent squared equals cosecant squared. So that's the identity I'm going to use. Cotangent squared x is cosecant squared x minus 1. So this is the integral of cosecant squared x minus 1. And that's helpful because cosecant squared is the derivative of something. It's the derivative of cotangent. So when I integrate this, I get negative cotangent because the derivative of cotangent is negative cosecant squared. And when I integrate minus 1, I get minus x plus c. No u sub needed because the angle was just x, so that's a nice easy one. All right, we have, this is kind of weird, 3 things happening right here. I think this is going to use a trig identity. Let's see. Theta, sine, cosine. And you're not going to have to know this trig identity for our AP test, as far as I know, or for my test. But let me try to remember this here. So sine of 2 theta is equal to 2 sine theta cosine theta. That was the double angle. That was the double angle identity that we had. So if we only have sine, cosine, then that means that's sine of 2 theta divided by 2. So let's rewrite that. So this is theta times sine 2 theta. And then the divided by 2, let's put the 1/2 out here. Now I have the product of 2 things. I have an algebraic and a trig. So I think I can do integration by parts on this. So again, I know you're going to be worried about like, oh my God, do I need to know the double angle identity? I don't think that you need to know the double angle identity for my test. I know you don't. I didn't use it. But it is good to know in general. Pythagorean, double angle, and the quotients and stuff are good to know. All right, so the derivative of theta, this is just like having an x because we're d theta. So that's 1, and the derivative of that is 0. The integral of sine of 2 theta. So the integral of sine will be negative cosine, and then there will be a negative 1/2 because there will be chain rule involved. Just like with e to the 2x, I got 1/2 e to the 2x. This will be negative 1/2 cosine of 2 theta. And then the integral of cosine is sine. There will be another 1/2 that comes out, so minus 1/4 sine of 2 theta. Plus, minus, plus. This gets us right down to our answer. So we have a negative theta cosine 2 theta over 2, and minus negative, so plus sine of 2 theta over 4 plus c. All right, I think I can finish this for my meeting. Let's see, we have 10 minutes. Okay, so for this one, I see something that I might want to try to factor, except it's not bottom heavy. Remember, partial fraction only works if it's bottom heavy, so you need to divide first. So I need to do some long division on this. Actually, I want to do that off to the side here. So x squared, divide it in the correct order. X squared plus 5x minus 24. We're going into x squared plus 0x plus 0. X squared gets multiplied by 1 to get x squared. Subtract all of this. 0 minus 5x is negative 5x. 0 plus 24 is plus 24. That's already the remainder. Don't write minus, write plus. Negative 5x plus 24 over x squared plus 5x minus 24. Okay, so I'm going to split this up. And this is now the integral of this expression. So I'm going to do the integral of 1 dx. I'm going to do that separately, plus the integral of negative 5x plus 24. And let's go ahead and factor this. It's x plus 8, x minus 3. Almost wrote 5. I just separated it out because I would have done these integrals separately. You could lump it all together still. The integral of 1 is x. That's the easy part. And then this is going to be, remember, the integral of something times 1 over x plus 8. And then the integral of something times 1 over x minus 3. And to find the something, we plug stuff in. So if x equals negative 8, let me do this off to the side so I have room to write my final. So if x equals negative 8, I cover up the x plus 8. I get negative 5 times negative 8 is 40. 40 plus 24 is 64. Over negative 8 minus 3 is negative 11. I don't think that simplifies very nicely, so that's just what I got. Weird. And then when I plug in x equals 3, I'm getting negative 15 plus 24. So that's 9. And then over 3 plus 8 is 11. Plus 9/11ths. It doesn't matter how ugly those fractions are. It's still easy to integrate. So x minus 64 over 11 ln of x plus 8 in absolute value plus 9/11ths ln of x minus 3 in absolute value plus c. All right, number 14 is already bottom heavy, so I can start by factoring. Well, I guess, and if I did u sub on this, I would get 2x minus 6, and then I only have an x up here. So again, I'm just going to do partial fraction on this one. And did that, let me go back. I keep going back to like, I could have done partial fraction on number 4. The reason u sub worked nicely is because I just got a derivative of 2x. It wasn't 2x minus 2 or anything like that. Okay, anyway, this is x minus 4, x minus 2. So we're going to split this into something from 0 to 1 of 1 over x minus 4 dx, and then something times the integral from 0 to 1 of 1 over x minus 2 dx. And then we'll use the cover-up method again. So if I plug in 4, I get 4 over 2, which is 2. If I plug in 2, I get 2 over negative 2, which is negative 1. And then my final is 2 ln absolute value x minus 4 minus ln absolute value x minus 2 plus c. Okay, the integral of 1 plus cosine x. 1 plus cosine is not an identity. What do we usually do when there's like weird trig happening like this? Usually we try some sort of trickery, like multiply by a conjugate or something. So I am going to do that. But I think I'm going to do it like times 1 minus cosine x underneath the square root. And if I do that to the top, I have to do it to the bottom. Honestly, I don't know if this is going to work. I don't have the answer key in front of me to see what I did. So I'm just going to try this. So this would give me the integral of the square root of 1 minus cosine squared x over square root of 1 minus cosine x. I think this is going to work. 1 minus cosine squared is sine squared. So this is really square root of sine squared. So now it's the integral of sine x over the square root of 1 minus cosine x. Now that I've manipulated it a bit, let's see if, I think u sub will work. U would be 1 minus cosine x. Du dx would be, so the 1 becomes 0. This becomes, sine x. So du over sine x will equal dx. So the sine x will cancel. So now it's the integral of 1 over square root of u du. This is the exponent rule here. So this is u to the negative 1/2. We add 1 to that, we get u to the 1/2. So 1 minus cosine x to the 1/2 divided by 1/2, or times 2, plus c. Oh, I just realized I forgot to evaluate back here. Whoops. Back here, there's no plus c. Evaluate from 0 to 1. So when you plug in 1, you get 2 natural log of 3, because there's an absolute value, minus natural log of 1. minus, plug in 0, 2 natural log of 4 minus natural log of 2. This is 0. I can distribute some stuff through, so that's 2 natural log of 3 minus 2 natural log of 4 plus natural log of 2. We could condense that if needed. Not going to take the time. All right, number 16. Let's see. I don't think we can just do u sub. Wait, can we do u sub? Oh, maybe we can do u sub. If we let u equal, let's let u equal, I think we had this in our notes, ln of sine x. I was about to do integration by parts, but maybe this will save us some of that. Du dx would be 1 over sine x times cosine x. So sine x times du over cosine x. Oh, no, that's not going to work. Will equal dx. That'll cancel my cosine, but it'll put an extra sign up there. What if u is just sine x? No, that's probably not going to be nice either. All right, fine. We'll do Liate. So I'm going to do it over here. I'm probably going to run out of room for this. I might have to. I'm going to do this problem, and then I'll do the next part in a video. So this would have to be ln sine x, and this would have to be cosine x. Derivative of this is 1 over sine x times derivative of sine, which is cosine x. Integral of cosine x is sine x. Plus, minus, loop. When you multiply those together, yeah, you'll just get cosine x dx because the signs will cancel. Okay, so that's not bad. So this is sine x times natural log of sine x. That's the first part. And then this minus the integral of cosine x dx, and we can integrate that. So sine x ln of sine x minus sine x plus c. All right, I have a meeting, so I'm going to stop the video here, and then I'll do another video for this last little section here.